Onto the example on page 90 of the first part of the notes. This one's called adding 1-100, and I've already created my .c file here. I've just the same procedure as before for creating the C file, and I'm going to hand you over to Mike, who's just going to tidy up that code and get that code running for us.
Okay, so everything here is should be nice and familiar to us now. We have an initialization declaration of a variable which is initialized to 0. We have a for loop that then reinitializes I. So it then creates an I variable and initializes it to 1. And what that's doing, so we have a look here. Okay, so we have a variable called sum initialized to 0, a variable called I initialized to 1.
Yep.
The comparison is less than or equal to 100, so we're going to increment it
So
by
it should
1
count from 1 to 100, that for loop.
should count from 1 to 100, and every time it iterates this loop,
Yep.
we're going to add 1 to sum.
So sum, no, I to sum.
Yes, we're going to add I
So
to
sum equals sum plus I. So as we go around that loop, it's going to be 1 plus 2 plus 3 plus 4 plus 5. So there's actually factorial
It's
as well.
factorial, yeah. So should we give that a quick run? GCC, we're going to call it adding, and we're going to do adding.c. Let's run that.
It's not factorial, it's a running sum of it.
So the running sum is 5050. That's interesting, isn't it? Let's have a look at how that's being built up, shall we?
Yeah, we could put a print statement in there, couldn't we?
Print
So if
statement.
we print the partial sum now,
Sum, so we'll add sum, like so, and then we're going to adding, and we're going to add what we're going to add on there, okay?
we'll put partial sum, because that's what it is.
Partial sum is equal to this, and we're going to be adding this, okay?
Yeah,
So
that's pretty neat. So we're going to see both numbers. We're going to see the partial sum, and we're going to see the number that we're adding into that partial sum.
yeah, and what we can also do is then here we can add adding, and then so the result would be, because we're going to do this before this happens, okay? And so then I'm going to add another one in there to say what the result is going to be. So we're going to predict the result, and we're going to put another %d there, and then in the variable here I'm actually going to do that calculation. So partial sum is going to show the current value of sum.
Yep.
Adding, and this is what we're going
That's
to
the
add
number
to
we're
it,
adding each time we go
and
around
then
the
our
loop.
result will actually be this before it's actually happened.
Yep.
Yeah?
Yep.
Okay, so let's try and run that. Okay. Right.
My word.
Let's have a look at this right from the beginning. Scroll up. So partial sum is currently 0. Starting, we're going to add 1, so the result is 1. Partial sum is 1. We're going to add 2. The result becomes 3. Partial sum is 3. We're going to add 3. The result becomes 6.
Absolutely incredible.
Absolutely incredible. We go all the way down.
How you can do something so complicated with just such few lines of code. Something's been haunting me a little bit, Mike, is that, for example, if I do this, because this window looks particularly slow to me, and I can't really work out why, because I know computers are blindingly fast. So say, for example, I put 10,000 on here. Now, for a computer to print 10,000 lines of code, I would assume that could do that a fraction of a second, so fast that I couldn't see it actually do it. But what happens when I do this look? So I'm going to build it again, and it was adding, wasn't it? So I've increased the loop size now to 10,000. Why is that so slow? Why does that take so long to do that 10,000 times? I would have thought that would do that in a millionth of a second.
It will do that in a millionth of a second. The reason it's so slow is because you're printing out the lines. If I take that away, if I comment that out,
okay,
and then run this, so I'm not getting that bit in the middle anymore, and then run it again, you're going to get immediate answer.
Isn't that clever? So what's happening there is actually you're using a serial communication into the command window, and the thing that's taking the time is to display the text on the screen, not to do the actual calculation.
Because there's a lot of background things going on. What we're doing is we're actually posting a message. As a multitasking operating system, we have to post a message to the operating system that we want to print on this terminal. Then we have to flush that situation, so that we have to wait for the operating system to actually draw that and do all kinds of internal things, draw it on the screen, show it on the console, and then tell us yes, it's on there. Then we will continue our execution.
So,
blocking in reality.
Yeah. So, actually, I mean, we do have debuggers for C and C++ and so on, but probably the type of debugging that most people are going to use, they're going to put print statements on the screen. But if you do, just be aware it's going to slow your code down, I think is the message there. So Mike's gone silly now.
I've gone silly. I've gone up to, I've gone up to a million, and I'm leaving this print statement off, and we're going to see how quickly it can actually do that. It's immediate.
My word, that's fast, isn't it?
Now let's just for
Let's do
fun
a
and
print statement in
amusement,
and go and get a cup of coffee and
let's actually see the difference. I mean, this is it's going to take some time, because every single line in effect does a blocking. See, that's interesting, isn't it? Do you see that?
It's rolling over, isn't it?
It's rolling over, and that's actually a way that we can fix that, because what this is doing. So we've got an
incorrect answer there, viewers. That what's happened there is every now and then you see a minus there. See the minus? That minus can't be true, because what you're printing in the first one there is the partial sum. So what's happened there, Mike?
It's showing a signed integer. What's happening there is it's showing a signed integer. So the way that integer values are represented can often include that the most significant bit is a signed bit. And so when that increments between 0 and 1, it changes the sign of the value.
So what you're telling me is that number's got too big to be held in an integer, right?
It's got too big to be held in a signed integer. So let's hold it, let's display it as an unsigned integer and see what we get there. So if we can fix that little problem there. Okay. Beautiful.
And lo and behold, we don't get that. What?
It's still rolling over. It's still rolling over, but now we're not flicking between sign, and it's rolling over because this is representing a 4-byte number, and the sum that we're producing over 1 million is becoming bigger than a 4-byte number.
So you're telling me that partial sum in there isn't actually correct, and you can see it's not, because it gets bigger and smaller. It should just get bigger and bigger. So how can we solve that?
Well, let's treat it as a long unsigned number, right, which is 8 bytes, and rather than having int here,
we're going to use a different type.
We're going to use a long.
Now you can have long int, or you can just have long, can't you?
So, okay, let's
go
with
just
long.
Just go for long.
And we're going to change this to a long as well. So
I don't think that one matters quite so much.
It didn't matter because we're only going up to 1 million.
But then we could go up to 100 billion or something.
Okay, let's run that.
So now the partial sum is just growing continuously, which is what we would expect.
Are we still flicking between in there? Looks like we are, didn't it? It's not getting any bigger.
Yeah, something funny going on there. Okay. Must be an error in your code, right?
It must be an error in my code. So we've got a partial sum, we're doing a long unsigned, and we're adding a long unsigned, and the result's a long unsigned. Sum is a long, I is also a long. It does seem valid to me.
Okay, so the compiler's interpreting, it's saying that we can't go any bigger than that.
It's actually, let's look at this number, let's look at the size.
236, it is going up.
It should be, I think what it is a printf library statement.
Can't accept anything larger than that.
It's getting quite big. Let's try and seems to get to 4, doesn't it?
Yeah.
And then,
Okay. Well, that's not our doing. That's the compiler. But it just goes to show that you need to be very careful with very large numbers, which is what we're dealing with there.
Yeah.
Okay, that's a brilliant bit of code there. We can have a lot of fun with for loops, and that's what happens when you want to do some proper calculation. Okay.